over a little bit. Can you go over that way a little bit? Alright, we're good. You can go back forward a little bit. Alright. Oh, too much. There we go. Carry on my way every time. Alright.
Hi, I'm Molly Vanderwerp.
And I'm Connor Steffens.
And today we will be diving into the life and work of Dutch mathematician Christiaan Huygens. Born April 14, 1629 into an influential family, Christiaan's early environment was the perfect catalyst for his later career in mathematics. His father, Christiaan Huygens, a diplomat and poet, was the friend and correspondent of many outstanding intellectual figures of the day, including the notable René Descartes and Galileo Galilei. Huygens studied the liberal arts from home until the age of 16, when he was sent to study law and mathematics at the University of Leiden.
Something of a classic Renaissance-era jack of all trades, Huygens dabbled in and contributed to many areas of study, including physics, mathematics, astronomy, and orology, the study of time. Today, we will focus on 4 of his most notable contributions. But first, we must travel back to France, where it all began.
When Galileo looked into the sky using one of his personal telescopes, he observed that Saturn was a planet that did not look like the others. It appeared to have an elliptical shape. It was later decided that the planet must have arms on its sides, but in the year 1655, Huygens and his brother, in a telescope of their own design, set out to tell a different story.
Brother Constantine, I have exciting news. Also, I need help.
Per usual, the telescope again, I presume? I suppose, but only if you need it.
So, recently I've been working on a new process to clean and polish the lenses in the telescopes so that the image is more focused. It is really fascinating because when...
You know I have no idea what you're talking about, right?
Right, sorry. It has to do with the eyepiece, you see. I've always owned a telescope with a single lens, but see how much clearer the image is when the machine has 2.
A compound lens? That's unheard of.
You bet, brother. 2 convex lenses. I just need some help putting it all together.
Alright, I'll try not to break anything.
What should we look at first?
How about Saturn? I heard that Galileo thinks it has arms sticking out of it.
Sure. Gee whiz, would you look at that? Arms. Well, actually, I'd almost describe them as rings. Thin, flat, nowhere touching rings.
That's preposterous. Well, would you look at that? Saturn really does have rings.
Wow! Huygens' discontent with the telescope and the telescope polishing process of his time led to him to design and perfect his own. Together with his brother Constantine, Huygens used a telescope of advanced accuracy to set his sights on Saturn, discovering that it had a ring of orbiting material.
Before Huygens' work with pendulums, most clocks were extraordinarily inaccurate. So much so, in fact, that they did not have minute hands. In 1657, Huygens contracted the construction of his pendulum design to clockmaker Salomon Koster, forever changing the world of timekeeping. Christiaan Huygens! How is my favorite Dutch mathematician doing this fine day?
I'm doing great, thank you. Excellent, even. I've got such a marvelous proposition for you. Here, just look at these.
Well, there's a lot of numbers on here, Christiaan, but I can't say I know what it means. 20 years of clockmaking, and I've never seen the likes of this.
It's a cycloid, Mr. Closter. Not a circular arc. Never a circular arc. A cycloid. This changes everything.
Slow down, Christiaan. Speak French, please.
Well, how do I explain? Well, we've always assumed that a pendulum motion would be graphed in circular arcs, correct?
Well, yeah, Galileo's idea, right?
Yeah, well, exactly, but pendulums move in cycloids. It's like the spokes on a wagon wheel, like tracing an arc as it rotates.
You're kidding. This does change everything. I'm not even sure I know how to construct this type of clock. Cycloids, to be sure.
Not to worry, I've done the math and...
Of course you have.
Okay, well, if you look at these equations, the time it takes for the arc to make one full motion is equal to 2 pi times the square root of the length over gravity.
Christiaan.
Right, sorry. So you're gonna need to change the dimensions of the clock as such.
Now this I can do. I hope you're right about this.
That makes two of us. Huygens' pendulum clock was far more accurate than anything else of his time. His design was perfect, give or take 10 seconds in a 24-hour day. This led to the addition of the minute hand on large household clocks, recently coined grandfather clocks. The concept of light and motion fascinated Huygens. However, his studies led to a conflict with another big-time physics rock star, Sir Isaac Newton.
Okay, see, that is exactly where you are wrong, Huygens. It doesn't work like that at all.
No, see, that is where you are wrong, Newton. Light is not actually made of particles. Instead, it is composed of waves.
Waves, you must be mad. Where is your proof?
Okay, look, here is what I've written down so far.
Every point on a wavefront may be considered a source of secondary spherical wavelets which spread out in the forward direction at the speed of light. The new wavefront is the tangential surface to all of these secondary wavelets. Okay, this is interesting, but what exactly do you mean?
Well, see, to put it simply, every point on a wavefront of light is a source of spherical wavelets, or particles. These wavelets spread out forward at the speed of light, and the new wavefront is a line tangent to all the wavelets.
Okay, interesting, but have you considered the processes of refraction? The entire color spectrum supports my theory of light as particles.
Okay, well, that is exactly what I have been wanting to discuss with you. Think about two adjacent rooms that are completely blocked off from each other, except for a slit in the room separating them. Now, if you put a lit candle in one room, the light in the adjacent room is not only represented by a slit on the opposite wall of the dark room. The room is also dimly lit on the other walls from the candle, even though there is no direct visual path from the candle to the wall. Therefore, light cannot be simply expressed as a particle, but rather as a wave that is emitted as a semicircle.
You do have a point there. I'm not ready to entirely disregard my theory of light as particles, but thank you for enlightening me.
Of course, Newton.
Huygens' wave theory of light was not as initially popular as Newton's, but has gained credibility over time. Modern chemistry and physics accept both theories. Light exists as both a particle and as a wave.
Nearly 20 years later, in 1691, a group of the world's most prominent thinkers in mathematics gathered to discuss a concept we now take for granted, the parabola, versus the catenary curve. A catenary is the idealized U-shape that a hanging chain assumes under its own weight, and is often used in the construction of bridges and arches. While many mathematicians at the time assumed said curve to be a parabola, Leibniz, Huygens, and Bernoulli thought otherwise.
I'm telling you, Christian, that just can't be.
Oh, but it is, Leibniz. They've been wrong all along. It's not a parabola, it's a catenary. See, if you observe this proof...
You may have tutored me in geometry, Huygens, but Galileo himself assured me of the shape. The hanging chain. It's a parabola.
Listen, Leibniz, if you take a hanging cord and assume these things, the cord depends on some gravity. Two weights attached to the cord can remain at rest only in one way, and the cord hangs a certain way regardless to where it is held.
Oh, I do see what you're getting at here. Why, we could derive an equation from this proof, could we not?
One step ahead of you, Leibniz. A catenary is similar to a parabola. Sure, but in essence, it's the curve that the focus of a parabola traces when you roll it.
Can you imagine the implications this has for calculating the lengths of curves? Integral calculus will change the world. And changed the world it did. Huygens' name today shows up in calculus, chemistry, and astronomy textbooks around the world, demonstrating the depth and breadth his discoveries made on a wide variety of subjects.
Not only did he have wicked cool hair, Huygens' work with telescopes in Saturn, light waves and optics, clocks and catenaries contribute to his lasting and widespread legacy. We're still going. We're still going.